Did I scare you? Anyway, moving on to 11.7, the last section of chapter 11 that we will be reviewing before the assessment for the test, unit test. And that is ratios of areas. So we're going to try to figure out a relationship between maybe a side length of a square or a triangle and then its area. So we can compare two rectangles or two triangles or two polygons and compare one side length to its area and see if we can just calculate an area without actually doing all the work of finding the actual formula and calculating it that way. So there is a relationship, we're just going to discover it. We're starting with this pizza problem, which was in your homework, in the book assignment, and a lot of you, or a few of you asked me about this if you got into that book assignment in class, and so I just wanted to come back to it again. And this is going to really relate to what we're learning today. So it says if 8 ounces of dough are needed to make a 10-inch pizza, how much dough will be needed to make a 20-inch pizza? So here you can see, well, a 10-inch pizza, that means that's the diameter. 10 inches is the diameter. So the radius is equal to 5. So if we're trying to find the area of that first pizza, then we need to do 5 squared times pi, which is 25 pi inches squared. The area of the 20-inch pizza, well, we know the diameter is 20, which means the radius is 10. Once again, the area is r squared times pi, which was 100 pi. Now, some of you might instantly see what the ratio is between these two. It says find the ratio of the area of the small pizza to the large pizza. So that ratio of small to large is just 25 pi to 100 pi. And if we reduce that, the pi's cancel. 25 goes into 100 4 times, so that's a 1:4 ratio. The small pizza is 1/4 the size of the large pizza, or what might be easier to understand is that the large pizza is 4 times bigger than the small pizza, right? So we can use this ratio to find out how much dough we would need to make the 20-inch pizza. So the 20-inch pizza, right, so we know that 8 ounces of dough is needed to make the small pizza. Sorry, I'm going to go back to my original relationship here. So I have small to large, and I said that ratio is 1:4. Well, 8 ounces is needed, and OZ is short for ounces, right? OZ is short for ounces, that's why I have an OZ there. So 8 ounces needed to make a small pizza, so the top row is small, and we're trying to discover how much is needed for the large pizza. So I'm just going to cross multiply. 1 times x is x, 4 times 8 is 32. So we would need 32 ounces to make the large pizza. Or in other words, we're just going to multiply that by 4 because the area is 4 times bigger, therefore we're going to need 4 times as much dough. So some people like to say, okay, well a 10-inch pizza went to a 20-inch pizza, that's twice as big, so I'm just going to multiply it by 2 and get 16 ounces. But that's not correct, because you're only thinking in one dimension here. You're just thinking in the diameter. And sure, you can roll out the 8 ounces of dough to make this diameter, and then if you wanted to make a 20-inch diameter twice that long, sure, you need another 8 ounces to get 16 ounces. But we're not talking about the diameter, we're talking about the actual area, right? So the area of the small one versus the area of the big one. So the relationship was 1 to 2, but to get the area relationship, we then square it to get our 4. So what is 2 squared? It was twice as big, the diameter was twice as big, therefore the area is 2 squared, which is 4 times as big. So that's what hopefully you'll notice as we go through these next problems. So the next few problems, you should be able to calculate these on your own. It would be good practice for you to practice using the triangle equations. So go ahead and pause and do A, B, and C on your own and see if you can come up with the conjectures or the theorems down there below. Okay, so let's see if you got the same ratios that I did or the same areas. So triangles with equal heights, that's our first experiment. So if we did triangle ABD, well my base was 4, my height was 4, so 4 times 4 divided by 2 was an area of 8. And then I did CBD, which is my red triangle. My base is 6, right? CD is my base. Now notice this is an obtuse triangle. So the height is not within this triangle, it's actually the same height out here, which goes from this vertex down to the extended base. So this is the height, which is still 4. So these two triangles, the blue triangle and the red triangle, have the same height right here. So equal heights, right? So we do 6 times 4 divided by 2, which has an area of 12. Then we were supposed to calculate the ratio of ABD to CBD. So I just did color coordinated here. 8 is to 12. I divided by 4. So my final answer was 2/3. So the ratio is 2 to 3. Okay, how about equal bases? This time we have an equal base, which means we have different heights. So the first one, ABC, was in blue, so my base is 10, and my height is right here, from the vertex to the base intersecting at 90 degrees. And 4 times 10 divided by 2 is 20. And then my ADC is the red triangle here, so the base is 10, but my height is 2 this time, right? From the vertex to the base intersecting at 90 degrees, 10 times 2 divided by 2 is 10. So what is the ratio? It is a 2 to 1 ratio. And then we got our similar triangles. So here you can clearly see base times height. 6 times 3 is 18. 18 divided by 2 is 9. And then the bigger one, 12 times 6 divided by 2 is 36. So that ratio is 9 to 36, which is a 1 to 4 ratio. Okay, so what, I guess is the question, right? Who cares? Well, let's see how that might help us. Let's compare the areas of the triangles. If two triangles have equal heights, so this is example 1, right? If two triangles have equal heights, then the ratio of their areas equals the ratio of what? So what else is 2 to 3 ratio? Well, hopefully you see here that it's the bases, right? So 4 to 6, well, reduce that, that's the same as 2 to 3. So their bases here are 4 and 6. They obviously have the same height, so these numbers are the same, but look at the other two numbers, it's their bases. So if two triangles have equal heights, then the ratio of their areas equals the ratio of their bases, the base of each triangle. If two triangles have equal bases, so this is example 2, right? Then their areas equal the ratio of, well, what do you think that's going to be? So they both had a base of 10, so in this formula you can see they both have a base of 10. Well, now we have their heights, which are a 4 to 2 relationship, and reduce that, and what do you get? You get the same ratio as their areas, which is a 2 to 1 ratio. So if they have the same base, then the ratio of their areas, then their areas equal the ratio of their heights. Now, what happened with similar triangles? That's not the case this time. It says if two triangles are similar, well, notice they're similar, but the red triangle here is only 2 times as big as the blue triangle, but their areas were 4 times bigger. So the red triangle's area was 4 times bigger than the blue triangle's area, but the dimensions were only twice as big. So it says if two triangles are similar, then the ratio of their areas equals the what of their scale factor? Their scale factor is 6 to 12, which is 1 to 2. So what do we do with 1/2? Well, you square it. If you square 1/2, 1 squared is 1, 2 squared is 4. So it's the square of their scale factor. So I give you one dimension here. If we square that relationship, we will get their area relationship. Same as the pizza problem we did at the very beginning. Okay, if you have questions, make sure you ask. So this one was example 3 from above, obviously. Okay, moving on with this investigation, you should try the investigation on your own. See if you can come up with all of the areas and the ratios, and see if you can fill out these down here. So go ahead and push pause and try this on your own. Okay, so you have to sketch a triangle with the width of 3 and a length of 5. So I'm going to make my width of 3 here and my length of 5 here. Sketch a similar rectangle, make the width of 9 and a length of 15. Okay, I'm not really going to have the space to do that, but let's pretend this is a width of 9 and this is a length of 15. Clearly not the case, but that's okay. I'll make this a little smaller. Okay, so it says, how do you know these shapes are similar? Well, how do I know? Because if I'm going to make a length of 9 and 15, 5 times 3 is 15, 3 times 9 is, 3 times 3 is 9, 5 times 3 is 15. They're both on a scale factor of 3. So this larger one is 3 times bigger than the smaller one. Calculate the area of the 3 by 15 rectangle. So that's obviously just 3 times 15, or 3 times 5, which is 15 units. 15 square units. Calculate the area of the large rectangle, so that's 9 times 15. 9 times 15, and that would just be 135 square units. Find the ratio of the small rectangle area to the large. That's a 15 to 135 ratio. It matters, right, which one's on top because it says small to large. So the small one has to be in the numerator and the large has to be in the denominator. So you do your reducing using your calculator math frac, and you see that the larger one is 9 times bigger in area than the small. So how does the area ratio compare to a ratio of the original side lengths? Well, we said the original side lengths 3 is to 9, that was a 1/3, right? The large one was 3 times as big. But the area is what? Well, it's this dimension squared. So it's the dimension squared. So down here, if the scale factor of two similar figures is A to B, then the ratio of their areas is A squared to B squared, or A squared to B squared, right? If we took 1/3 and squared it, 1 times 1, 3 times 3, that would give me my area ratio. Okay, but what about perimeter? So calculate the perimeter of the small rectangle, so that's 2 times 3 plus 2 times 5, so 10 plus 6 is 16. The perimeter of the large rectangle, that's 2 times 9 plus 2 times 15, that's 30 plus 18, which is 48. So the ratio would be 16 to 48, which is a 1 to 3 ratio. Well, how does this compare? It's actually the same, right? Because we're just talking one-dimensional here. So the side lengths are one-dimensional to one-dimensional. We're not doing this two-dimensional part with area. So therefore, they're in the same. The ratios of the perimeter is just simply A to B. It's same as the same ratio. It's the same ratio as the sides are to each other. So the perimeter ratio is the same as the side ratio. All right, with that, let's see if you can answer these questions down here. Push pause and then come back and see how you do. Okay, how'd it go? So the ratio of corresponding heights of two similar triangles is 3 to 5. So corresponding heights of two similar triangles is 3 to 5. What is the ratio of their corresponding sides? Well, if their heights are 3 to 5, then their corresponding sides have to be the same because they're similar triangles. And we're still talking about the dimensions of the triangle itself, right? Heights and sides, those are just dimensions of the triangle, so they have to be in the same ratio if they're similar. Perimeter, we just said, if the ratios are the same from one triangle, or if the ratios, from one triangle to the next are 3 to 5, then the perimeters have to be that same ratio as the sides are. So as the heights are, or as one of the dimensions is, whether it's both heights or both bases or both sides. But the areas, we just said, if the scale factor of two similar triangles is A to B, then their areas must be A squared, B squared, which would be 9 to 25. So we square 3, we get 9, we square 5, which is 25. Okay, if you have questions, ask me in class. The bottom ones were true, true, false, true. True, true, false, true. It says so why is this one false? Ooh, that's the question. It says if the ratio of the perimeters of two rectangles is 4 to 7 and the ratio of their areas is 16 to 49. Come up with a counterexample. Okay, so I like to do 1, 1, 1, 1. That perimeter is 4. I need to make one with a perimeter of 7. Okay, so I'll make that 2, 2, 1.5, 1.5. Well, what's wrong with these rectangles? This is missing the word similar. It doesn't say that those rectangles are similar, therefore it's false. Bye.